Testing, can you hear me? Testing again, can you hear me? Testing one last time. Alright, this video is public now, so I'm going to be reading the computer architecture book again. Last stream, I finished reading about the memory system. I was reading about virtual memory. This time, I'm going to be reading about the multiprocessor system. Okay, let's just start. Up till now, we have discussed the design and implementation of a processor in great detail, including several methods to optimize its performance, such as pipelining. We observed that by optimizing the processor, the memory system, it is possible to significantly increase the performance of a program. Now the question is this enough, or is it possible to do better? Short answer to this question is maybe not. For a long answer to this question, the reader needs to read through this entire chapter and possibly take a look at the references. Let us start out by saying that a processor performance has its limits. It is not possible to increase the speed of a processor indefinitely. Even with very complicated superscalar processors and highly optimized memory systems, it is typically not possible to increase the instruction per cycle by more than 50%. Secondly, because of the power and temperature considerations, it is very difficult to increase processor frequency beyond 3 GHz. The reader should note that processor frequencies have remained more or less the same over the last 10 years. Consequently, CPU performance have also been increasing very slowly over the last 10 years. We illustrate these points in figure 12.1, 12.2, and 12.1 and 12.2. Figure 12.1 shows the peak frequency of processors released by multiple vendors such as Intel, AMD, Sun, from 2001 to 2010. Clock frequency, megahertz. These are CPU frequencies. 3000 megahertz, 5000 megahertz. Then this is the CPU performance. We observe that the frequency has stayed more or less constant. The trends do not indicate a gradual increase in frequency. We expect that in the near future also the frequency of processors will be limited to 3 GHz. Figure 12.2 shows the average spec Intel 2006 score for the same set of processors from 2001 till 2010. We observe that CPU performance is slowly saturating over time, and it is getting increasingly difficult to increase performance. Yep, it's plateauing. Even though the performance of a single processor is not expected to significantly increase in the future, the future of computer architecture is not bleak. This is because processor manufacturing technology is steadily getting better, and this is leading to smaller and faster transistors. Till the late 90s, processor designers were utilizing the gains in transistor technology to increase the complexity of a processor by implementing more features. However, due to limitations in complexity and power, designers resorted to using simpler processors after 2005. Instead of implementing more features in processors, vendors instead decided to put more than one processor on a single chip. This helps us run more than one program at the same time. Alternatively, sometimes it is possible to split a single program into multiple parts and run all the parts in parallel. This paradigm of using multiple computing units running in parallel is known as multiprocessing. The term multiprocessing is a rather generic term. It can either refer to multiple processors on the same chip working in parallel, or it can refer to multiple processors across chips working in parallel. So, multiple processors in the same chip or multiple processors across chips. Or, like if there are multiple chips, a multiprocessor is a piece of hardware that supports multiprocessing. When we have multiple processors within a chip, each processor is known as a core, and the chip is called a multi-core processor. The term multiprocessing refers to multiple processors working in parallel. This is a generic definition and can refer to multiple processors on the same chip or processors across different chips. A multi-core processor is a specific type of multiprocessor that contains all of its constituent processors in the same chip. Each such processor is known as a core. Right? So in the late 60s and 70s, large computers were primarily used by banks and financial institutions. They had a growing base of consumers, and consequently, they needed computers that could perform more and more transactions per second. Typically, just one processor proved to be insufficient in providing the computing throughput that was required. Hence, early computer designers decided to put multiple processors in a computer. Processors could share the computing load and thus increase the computing throughput of the entire system. One of the earliest multiprocessors was the Burroughs 5000, which had two processors, A and B. A was the main and B was the auxiliary. When the load was high, processor A gave processor B some work to do. Almost all of the major vendors at that time also had multiprocessor offerings such as IBM 370, PDP 11, and VAX 11782, and UNIVAC 1108 2. These computers supported a second CPU chip. This was connected to the main processor. In all of these early machines, the second CPU was on the second chip that was physically connected to the first with wires or cables. They came in two flavors, symmetric and asymmetric. A symmetric multiprocessor consists of multiple processors where each processor is of the same type and has access to the services offered by the operating system and peripherals, whereas an asymmetric multiprocessor assigns different roles to different processors. There is typically a distinguished processor that controls the operating system and the peripherals. The rest of the processors are slaves. They take work from the main processor and return the result. Symmetric processor, each processor is of the same type. An asymmetric processor assigns different roles to different processors. So the symmetric paradigm tells all the constituent processors in a multiprocessor system as the same. It treats all the constituent processors in a multiprocessor system as the same. Each processor has equal access to the operating system and the I/O peripherals. These are known as symmetric multiprocessing system. So asymmetric, this paradigm does not treat all the constituent processors in a multiprocessor system as the same. There's typically one master processor that has exclusive control of the operating system and I/O devices, designs work to the rest of the processors. In the early days, the slave processors were connected to the main processor using a set of cables. It was typically housed in a different area of the main computer. Note that in those days, computers used to be the size of a room. With increased miniaturization, all the processors started coming closer. In the late 80s and early 90s, companies started putting multiple processors on the same motherboard. A motherboard is a printed circuit board that contains all the chips that a computer uses. The reader can take the lid off her laptop or desktop. The large green board with chips and metallic lines is the motherboard. By the late 90s, it was possible to have 4 or 8 processors on a single motherboard. They were connected to each other using dedicated high speed buses. Gradually, the era of multi core processors commenced. It is now possible to have multiple processors in the same chip. IBM was the first to announce a dual core multi core processor called the Power 4 in 2001. Intel and AMD followed with similar offerings in 2005. As of 2012, 8 core and 10 core versions of multi core processors are available. And let me see. A motherboard is a printed circuit board that contains all the chips that a computer uses. It is possible to have 4 or 8 processors on a single motherboard. Okay. Let us now take a deeper look at what happened between 1960 and 2012 in the world of processors. In the 60s, a computer was typically the size of a room. And today, a computer fits in a pocket. A processor in a cell phone is around 1.6 million times faster than the IBM 360 machines in the early 60s. It is also several orders of magnitude more power efficient. The main driver for this continued evolution of computer technology is the miniaturization of transistors. Transistors used to have a channel length of several millimeters in the 60s. And now they're about 20 to 30 nanometers long. In 1971, a typical chip used to have 2,000 to 3,000 transistors. Nowadays, a chip has billions of transistors. Over the last 40 to 50 years, the number of transistors per chip has been roughly doubling every 1 to 2 years. In fact, the co-founder of Intel, Gordon Moore, had predicted this trend in 1965. The Moore's law predicts that the number of transistors on a chip is expected to double every 1 or 2 years. Originally, Morse had predicted the period of doubling to be every year. However, over time, this period has become about 2 years. This was expected to happen because of the steady rate of advances in manufacturing technology, new materials, and fabrication techniques. In 1965, Gordon Moore conjectured that the number of transistors on a chip will be doubled roughly every 1 to 2 years. Initially, the number of transistors was doubling every year. Gradually, the rate slowed down to 18 months. Now it is about 2 years. Moore's law has approximately held true since it was proposed in the mid 60s. Nowadays, almost every 2 years, the dimension of transistors shrinks by a factor of root 2. This ensures that the area of the transistor shrinks by a factor of 2, and thus it is possible to fit twice the number of transistors on a chip. That is, define the feature size as the size of the smallest structure that can be fabricated on a chip. Table 12.1 shows the feature sizes of Intel processors over the last 10 years. We observe that the feature size decreases by a factor of roughly root 2 every 2 years. This results in a doubling of the number of transistors. It gets smaller and smaller every 2 years, right? And they're able to fit in more transistors. Now that Moore's law is an empirical law, owing to the fact that it has predicted trends correctly for the last 40 years. It is widely quoted in technical literature. It directly predicts a miniature in the transistor size. Small transistor is more power efficient and faster. Designers were traditionally using these benefits to design bigger processors with extra transistors. They were using additional transistor budget to add complexity to different units, increase cache sizes, increase the issue width, and the number of functional units. Secondly, the number of pipeline stages were also steadily increasing up till about 2002. There was an accompanying increase in the clock frequency also. However, after 2002, there was a radical change in the world of computer architecture. Suddenly, power and temperature became major concerns. Processor power consumption figures started to exceed 100 watts, and our chip temperature started to exceed 100 degrees. These constraints effectively put an end to the scaling and complexity and clock frequency of processors. Instead, designers started to pack more cores per chip without changing its basic design. This ensured that the number of transistors per core remained constant. And according to Moore's law, the number of cores doubled once every 2 years. This started an era of multi-core processors. And the processor vendors started doubling the number of cores on chip. As of 2012, we have processors that have 8 to 10 cores per chip. The number of cores per chip are expected to reach 32 or 64 in the next 5 to 10 years by 2020. It's 2026 now. A large multi-core processor today has multiple cores per chip and multiple chips per system. For example, your author is at the moment writing this book on a 32-core server. It has 4 chips, and each chip has 8 cores. Along with the regular multi-core processors, there has been another important development. Instead of having 4 large cores per chip, there are architectures that have 64 to 256 very small cores on a chip, such as graphic processors. These processors also follow the Moore's law and are doubling their cores every 2 years. Such processors are increasingly being used in computer graphics, numerical, and scientific computing. It's also possible to split the resources of a processor to make it support 2 program counters and run 2 programs at the same time. Such processors are known as multi-threaded processors, and it is not possible to cover the entire design space of multiprocessors in this book. Okay, so software for multiprocessor systems loosely couple multiprocessing. There are 2 primary ways to harness the power of multiprocessors. First method is to run multiple unrelated programs in parallel. For example, it is possible to run a text editor and a web browser at the same time. Editor can run on process 1 and the web browser can run on process 2. Both of them can occasionally request for OS services and connect to IO devices. Users often use large multiprocessor systems containing more than 64 to 128 processors to run a set of jobs that are unrelated. For example, a user might want to conduct a weather simulation with 128 different sets of parameters. Then she can start 128 separate instances of the weather simulation software on 128 different processors on a large multiprocessor system. We thus have a speed up of 128 times as compared to a single processor system, which is significant. This paradigm is known as loosely coupled multiprocessing. Here, the dependencies between programs is almost negligible. Note that using a multiprocessor in this manner is not conceptually very different from using a cluster of computers that compromises completely unrelated machines that communicate over a local area network. The only difference is that the latency between machines in a multiprocessor is lower than that in cluster computers. A loosely coupled multiprocessor such as a cluster of PCs is known as a multicomputer. A multi-computer consists of a set of computers typically connected over the network. It is capable of running a set of programs in parallel, where the programs do not share their memory space with each other. It is capable of running a set of programs in parallel where they do not share the same memory space. Okay. However, the real benefit of a multiprocessor is occurred when there is a strong degree of overlap between different programs. This paradigm is known as a strongly coupled multiprocessing. Here, programs can share their memory space, file, and network connections. This method of using multiprocessors harnesses their two power and helps us speed up a large amount of existing software. The design and programming of strongly coupled multiprocessors is a very rich field and is expected to grow significantly over the coming decade. So over here, we are running a set of programs in parallel that share their memory space, data code file, and network connections. This book, we shall mainly look at strongly coupled multiprocessing. Okay. Shared memory versus message passing. Let us now explain the methods of programming multiprocessors. For ease of explanation, let us draw an analogy here. Consider a group of workers in a factory. They cooperatively perform a task by communicating with each other orally. A supervisor often issues commands to the group of workers and then they perform their work. There is a problem, a worker indicates it by raising an alarm. Immediately, other workers rush to his assistance. In the small and simple setting, all the workers can hear each other and see each other's actions. This proximity enables them to accomplish complex tasks. You can alternatively consider another model where workers cannot necessarily see or hear each other. In this case, they need to communicate with each other through a system of messages. Messages can be passed through letters, phone calls, or emails. In this setting, if a worker discovers a problem, he needs to send a message to a supervisor such that she can come and rectify the problem. Workers need to be typically aware of each other's identities and explicitly send messages to all or a subset of them. It is not possible anymore to shout loudly and communicate with everybody at the same time. However, there are some advantages of this system. We can support many workers because they do not have to be co-located. Secondly, since there is no constraint on the location of workers, they can be located at different parts of the world and be doing very different things. This system is thus far more flexible and scalable. Inspired by these real life scenarios, computer architectures have designed a set of protocols for multiprocessors following different paradigms. First paradigm is known as shared memory, where all the individual programs see the same view of the memory system. Program A changes the value of x to 5, then program B immediately sees the change. Second setting is known as message passing. Here multiple programs communicate among each other by passing messages. Shared memory paradigm is more suitable for strongly coupled multiprocessors, and message passing paradigm is more suitable for loosely coupled multiprocessors. Note that it is possible to implement message passing on a strongly coupled multiprocessor. Likewise, it is also possible to implement an abstraction of a shared memory on an otherwise loosely coupled multiprocessor. This is known as distributed shared memory. However, it's not the norm. Okay, wait. Let me see, reread this again. So, group of workers in a factory communicate with each other orally, and there's a supervisor. In case if there's any problem, the problem goes to the supervisor. If there's a problem, we raise an alarm. Okay, so all the workers in this setting, all the workers can hear each other and see each other's actions. Now we are considering another model where workers cannot see or hear each other. We need to communicate through other means. So if a worker discovers a problem, he sends a message to the supervisor. Workers can send a message to one or more of them. Wait, you can support many more workers because they do not have to be co-located. So there's no constraint on the location. First paradigm is known as shared memory, where all individual programs see the same view of the memory system. The second setting is known as message passing. Okay, so this paradigm is known as shared memory. This paradigm is known as message passing. So strongly coupled multiprocessor. Shared memory paradigm is more suitable for strongly coupled multiprocessors. Okay. Message passing paradigm is more suitable for loosely coupled multiprocessors. Let us try to add n numbers in parallel using a multiprocessor. Code for it is shown in example 149. We have written the code in C++ using OpenMP language extension. Let us assume that all the numbers are already stored in an array called numbers. The array numbers has size entries, and assume that the number of parallel subprograms that can be launched is equal to n. Partial sums, numbers, result. Initialize the array, and this is the parallel section. What is this? Get my processor ID, add my proportion of numbers. Write a shared memory program to add a set of numbers in parallel. All the numbers are already stored in an array called numbers. Okay, we have the starting index, my ID plus my ID times size divided by n. And the n index is starting index plus this. Start index, end index. Okay, we have a bunch of numbers. They stored in this array, numbers, size. We have partial sums, which is equal to n, which has the size of n. N is smaller than size. Okay, so what I think is happening, wait, can I, we have numbers, right? And then we have partial sums. Like, let's say, we have numbers with lots of numbers. Let's say there are a bunch of numbers in here, like a subset in here, a subset in here, subset in here, and a subset in here, like a bunch of numbers in here, bunch of numbers in here, bunch of numbers in here, bunch of numbers in here. This is the numbers array, this big one. I think what they're doing is taking this subset, putting it over here. This array size has size 4, Well, in this example, it has size 4. And this over here has a size. But we are partitioning it using size divided by 4, like these partitions. We are taking all the numbers in these and storing it here. Taking all the numbers in these, storing it in here. All the numbers in these, storing it in here. Taking all the numbers in these, storing it in here. And at the end, we are looping through this much smaller array. And then storing it in result. It is easy to mistake the code for a regular sequential program except for the directive pragma on parallel. This is the only extra semantic difference that we have added in our parallel program. Launches each iteration of this loop as a separate subprogram. Each such subprogram is known as a thread. I've never seen this before. A thread is defined as a subprogram that shares its address space with other threads, communicates with them by modifying the values of memory locations in a shared memory space. Each thread has its own set of local variables that are not accessible to other threads. The number of iterations or the number of parallel threads that can launch in a system parallel that is set in advance. But how do you specify how many threads to make? The number of iterations or the number of parallel threads that gets launched is the system parameter that is set in advance. Oh, it is set in advance. It's typically equal to the number of processors. In this case, it is equal to n. Thus, n copies of the parallel part of the code are launched in parallel. Each copy runs on a separate processor. Now that each of these copies of the program can access all the variables that have been declared before the invocation of the parallel section. For example, they can access partial sums and the numbers array. Each processor invokes the function in the ARM getThreadSum, which returns the ID of the thread. Each thread uses the thread ID to find the range of the array that it needs to add. It adds all the entries, the relevant portion of the array, and saves the result in the corresponding entry in the partial sums array. Once all the threads have completed their job, the sequential section begins. This piece of sequential code can run on any processor. This decision is being made dynamically at runtime by the operating system or the parallel programming framework. To obtain the final result, it is necessary to add all the partial sums in the sequential section. A thread is a subprogram that shares its address space with other threads. It has a dedicated program counter and a local stack that it can use to define its local variables. You can refer to a thread as a software thread to distinguish it from hardware thread that we shall define later. A graphical representation of the computation is shown in figure 12.3. So graphical representation of the program to add numbers in parallel. Parent thread, initialization, spawn child threads run, thread join operation, and then the sequential section. A parent thread spawns a set of child threads. They do their own work and finally join when they're done. Parent thread takes over and aggregates the partial result. There are several salient points to note here. The first is that each thread has a separate stack. A thread can use its stack to declare its local variables. Once it finishes, all the local variables in its stack are destroyed. To communicate data between the parent thread and the child thread, it is necessary to use variables that are accessible to both the threads. These variables need to be globally accessible by all the threads. Child threads can freely modify these variables and even use them to communicate among each other also. They're additionally free to invoke the operating system and write to external files and network devices. Once all the threads have finished executing, they perform a join operation and free their state. The parent thread takes over and finishes the role of aggregating the results. Here, join is an example of a synchronization operation between threads. There can be many other types of synchronization operations between threads. All that the reader needs to understand is that there are a set of complicated constructs that threads can use to perform very complicated tasks cooperatively. Adding a set of numbers is a very simple example. Multi-threaded programs can be used to perform other complicated tasks such as matrix algebra and even solve differential equations in parallel. Let us now briefly look at message passing. Note that message passing based loosely coupled systems are not the main focus area of this book. Hence, we shall give the reader a flavor of the message passing programs. Note that in this case, each program is a separate entity and does not share code or data with other programs. It is a process, where a process is defined as a running instance of a program. Typically, it does not share its address space with any other process. Let us now quickly define our message passing semantics. We shall primarily use two functions, send and receive, as shown in table.point2. Send PID value, receive from PID. The send function is used to send an integer to a process whose ID is equal to PID. The receive is used to receive an integer sent by the process whose ID is equal to PID. PID is equal to any source, and then the receive function can return the value sent by any process. Our semantics is on the lines of the popular parallel programming framework, MPI, message passing interface. MPI calls have many more arguments, and their syntax is much more complicated than our simplistic framework. Let us now consider the same example of adding in numbers in parallel in example 150. This is supposed to be 150. Yeah, it is. Send and receive call. So send function send an integer to a process. Receive an integer from a process. The function blocks till it gets the value. If PID is equal to any source, then the receive function returns with the value sent by any process. What do they mean by this, any source? Like the string any source? Or is there like a predefined macro called any source? Write a message passing based program to add a set of numbers in parallel. Make appropriate assumptions. Let us assume all the numbers are stored in the array. And numbers in this array is available to all the n processors. So the array is called numbers. Okay. Let the number of elements in the numbers array be size. For the sake of simplicity, let us assume size is divisible by n. So spawn all parallel processes. Wait, we aren't using threads anymore. Oh yeah, they talked about processes. Okay. For each process, execute the following code. Int my ID, get my process ID. Compute the partial sums. On the non-root nodes, send their partial sums to the root. If my ID is not 0, send the partial sum to the root. Else, you have sum which is partial sum, which is its own partial sum, right? No, partial sum is, partial sum is 0. Wait. Each process has their own partial sum, right? And size and n are global. Wait, size and n. So all processes have their own stack, so they have their own partial sum. Even the root one, it has its own partial sum. And then receive any source. The root one has this sum variable which starts with partial sum, and then it receives all the partial sum from all the other processes, right? Let me see. Oh yeah, send over here. And then shut down all processes, return sum. Receive any source. And this will happen n times. Okay. Can't we just do this? Wait, no, that doesn't make sense. All right. Amdahl's law. We have just taken a look at examples for adding a set of n numbers in parallel using both the paradigms, namely shared memory and message passing. We divided our programs into two parts, a sequential and a parallel part. In the parallel part of the execution, each thread completed the work assigned to it, created a partial result. In the sequential part, the root or master or parent thread initialized all the variables and data structures and spawned all the child threads. After all the child threads completed, the parent thread aggregated the results produced by the child threads. This process of aggregating results is known as reduction. Process of initializing variables and reduction are both sequential. Let us now try to derive the speedup of parallel program. What? Vis-a-vis its sequential counterpart. Let us consider a program that takes t sequential units of time to execute and let f sequential be a fraction of time that it spends in its sequential part. And 1 minus f sequential be the fraction of time it spends in its parallel part. Why is this t sequential? You're considering the whole program, right? Not just the sequential part. The sequential part is unaffected by parallelism. However, the parallel part gets equally divided among the processors. If we consider a system of p processors, then the parallel part is expected to have a speedup of p times. Thus, the time p parallel that the parallel version of the program takes is equal to p parallel. Is this time for only the sequential part? So time, within each parallel there are sequential lines, but they're sequential for that particular thread, right? The time sequential. Okay, so the fraction of sequential and the fraction of parallel. Fraction of parallel. It spends this much time in the parallel part. Why are we dividing it by p? I think they're talking about the total time, like all the parallel paths take up. All this divided by p plus f sequential, and then times it by sequential unit of time. We get t parallel. That the parallel version of the program takes is equal to this much. Alternatively, the speed up s is given by sequential divided by the parallel is equal to this. Hold on, let me think about this. T sequential. Wait. We have a program. Program has a parallel part and a sequential part. And let's say this is the parallel part. This is the sequential part, the parallel part. And the program has a lines of code. Yeah, let me think about this. So out of all of wait, we have fraction of time that it spends in its sequential part, and let this be the fraction of time that it spends in its parallel part. Um okay, if this wasn't, we know it. Okay, I think consider program that takes the sequential units of time to execute. It's like if we executed all of this sequentially by one thread plus all of this part which is executed sequentially. That is this over here. So we take this fraction, added by this fraction, but since it's being run by multiple processors, we divide it by p. And the total fraction. Okay, wait, hold on. I think t sequential is like as if the entire program was running sequentially without the parallel aspect. Like like what we talked about over here, as if this entire thing was being run sequentially without any of the parallel aspect. That's desequential. And the total fraction times desequential gives the deparallel. Yeah, I think that's what this is. Equation 12.2 is known as Dahl's law. It is a theoretical estimate of the speedup that we expect with additional parallelism. We get 12.4 plus the speedups as predicted by Dahl's law for three values of f sequential 10%, 5%, and 2%. We observe that by increasing with an increasing number of processors, the speedup gradually saturates and tends to a limiting value 1 over f sequential. We observe diminishing returns as we increase the number of processors beyond a certain point. For example, if f sequential is 5%, then there is no appreciable difference in speedups between a system with 35 processors and a system with 200 processors. Okay. We approach similar limits for all three values of f sequential. The important point to note here is that increasing speeds up by additional processors has its limits. We cannot expect to getting speedups indefinitely by adding more processors because we are limited by the length of sequential sections and programs. To summarize, we can draw two inferences. First is that to speed up a program, it is necessary to have as much parallelism as possible. Hence, we need to have a very efficient parallel programming library and parallel hardware. However, parallelism has its limits, and it is not possible to increase the speedup appreciably beyond a certain limit. Speedup is limited by the length of the sequential section in the program. To reduce the sequential section, we need to adopt approaches both at an algorithmic level and at system level. We need to design our algorithms in such a way that the sequential section is as short as possible. Secondly, we need a fast processor that can minimize the time it takes to execute a sequential section. We looked at a later requirement in chapters 9, 10, and 11. Now let us look at designing fast and power efficient hardware for parallel sections. Design space of multiprocessors. Michael J. Flynn proposed the famous Flynn's classification of multiprocessors in 1966. He started out by observing that an ensemble of different processors might either share code, data, or both. There are four possible choices: single instruction, single data, single instruction, multiple data, multiple instruction, single data, and multiple instructions, multiple data. SIST, this is a standard uniprocessor with single pipeline as described in chapter 9 and 10. SIMD can have multiple streams of data in a single instruction. For example, an SIMD instruction can add one set of numbers with a single instruction. Modern processors incorporate SIMD instructions in the instruction set and have special SIMD execution units also. Examples include x86 processors that contain SSE set of SIMD instruction sets. Graphic processors and vector processors are special examples of highly successful SIMD processors. So multiple instruction, single data, they're very rare. They're mostly used in systems that have a very high reliability requirements. For example, large commercial aircrafts typically have multiple processors running different versions of the same program. Final outcome is decided by voting. A plane might have a MIPS processor, an ARM processor, and an x86 processor, each running different versions of the same program, such as an autopilot system. Here we have multiple instruction streams, yet a single source of data. A dedicated voting circuit computes a vast majority of three outputs. For example, it's possible that because of a bug in a program or the processor, one of the system can erroneously take a decision to turn left. However, both of the other systems might take the correct decision to turn right. In this case, the voting circuit will decide to turn right. Since MIST systems are hardly ever used in practice other than such specialized examples, we will not discuss them anymore in this book. Multiple instructions, multiple data. So this by far are most prevalent multiprocessor systems today. There are multiple instruction streams and multiple data streams. Multi-core processors and data servers are all MIMD systems. Examples 149 and 150 pertain to MIMD systems. We need to carefully examine the meaning of multiple instruction streams. This means that instructions come from multiple sources. Each source has its unique location and associated program counter. Two important branches of MIMD paradigm have formed over the last few years. First is single program multiple data. Second is multiple program multiple data. Most parallel programs are written in single program multiple data. Here, multiple copies of the same programs run on different cores or separate processors. However, each individual processing unit has a separate program counter and thus receives a different instruction stream. Sometimes SPMT programs are written in such a way that they perform different actions depending on their thread IDs. We saw a method in example 149 on how to achieve this using OpenMP functions. The advantage of SPMT is that we do not have to write different programs for different processors. Parts of the same program can run on all the processors, though their behavior might be different. A contrasting paradigm is MPMT. Here, the paradigms running on different processors are actually different. Here, the programs running on different processors are actually different. They are more useful for specialized processors that have heterogeneous processing units. There is typically a single master program that assigns work to slave programs. The slave programs complete the quanta of work assigned to them and then return the results to the master program. The nature of work of both the programs is actually very different, and it is often not possible to seamlessly combine them into one program. From the above description, it is clear that the system that we need to focus on are SIMD and MIMD. MIST systems are very rarely used and thus will not be discussed anymore. Let us first discuss MIMD multiprocessing. Note that we shall only describe SPMD variant of MIMD multiprocessing because it is the most common approach. MP, so multiple program, multiple data. Different processors are, the programs running on different processors are actually different. All right. And with single program, multiple data, each individual processing unit has a separate program counter and thus receives a different instruction stream. Wait, so when they're updating the counter, updating the program counter, how do they do it? Do they like, instead of adding, incrementing it by 1, they like add 4 to it? Or they add like a large number? Sometimes SPMD programs are written in such a way that they perform different actions depending on their thread IDs. Okay, I will end the stream here. And I will continue reading the rest of the book next stream. Right then, see you guys next time. Bye.